Hi. Well, let's just let everybody clear out or come in first. Before I start, basically, I have 3 questions for you guys. Simple questions, not trick questions. First question is, can I have a raise of hands how many people who are familiar with cryptography? Okay, great. We've got some good ones here. And second question, how many people are familiar with how a mainframe works? Oh, okay. Okay, this is a dangerous group here. I'm going to stand far away. And third question is, how many people here are familiar with how artificial intelligence works? Oh my God, okay. Don't bring the microphone to him. All right, okay, let me start now then. Good afternoon, and thank you for choosing this session, because you actually have a choice of 2. One, the one above was actually an imaginary use case, and this one is actually a real use case. So I'm Huang. I'm from Swedbank. Swedbank is one of the largest banks in Sweden. But we don't just operate in Sweden. We also operate in Estonia, Latvia, as well as Lithuania. So you can imagine the number of credit card processing we have just coming in every day. Oh, just to mention, I have a fantastic colleagues here as well. There's Hannah, there's Eric, and there's Dimitri. Say hi to them later on. Right, so what is this session about? I'm just going to zoom in directly. Right, exactly what we're doing is we're focusing on PCI DSS version 4, requirement 12, and 3.3. Very specifically, this particular statement here that deals with an up-to-date inventory of all cryptographic cipher suites and protocols in use, including purpose and where it's used. Okay, why is this important? Okay, other than it's in the PCI specification, is this a real threat? And answer is actually yes. In this morning's session, the PCI manager mentioned about quantum computers. And quantum computers is actually quite real. In the US, the US Department of Commerce has actually tasked and created the new FIPS specification for the new quantum resistance algorithms to replace the existing algorithms. So the ones that we use today in the banks, like RSA, DS and everything. So this, in theory, can be broken by the quantum computer in time to come, or imminent danger. So that's so the interesting thing is there's actually a parallel with that and this one. So there in the US, they also have to start getting a cryptographic inventory. And the reason is partly because President Biden, he was spearheading this thing where the government agencies were supposed to start gathering cryptographic inventory of everything that they're using to be prepared to do the migration of all their cipher suites to a quantum-resistant algorithms. So the next thing here in 12.3.3 is how do you actually approach this testing procedure? So the exact phase here is to examine the documentation for this and use and interview the personnel to verify the document reviews in accordance with elements specified in this requirement. It's a very simple sentence, but if you study what happened in the US when the federal agencies tried to do this, it was a chaotic mess. So there's a lot of good lessons to be learned from there. The key thing is that they found that it was really challenging because even though the US federal government agencies, they're not PCI standard, but they actually are big. They are very big. They have software from everywhere. They have legacy softwares, softwares that predates this, so they literally have no documentation of cryptography other than encryption is available. They use third-party software. They use third-party libraries. They use a different type of languages, so for them to get the information was not easy. And one of the things for the documentation, so what they did was they actually started going to the vendors to get the documentation. And the vendors themselves also don't have this cryptographic thing in mind. So what they have is like a car showroom documentation. You get it, they tell you what's the top speed of the car. But they don't tell you that this is only available if you buy the turbo option and something else. So as a result, the documentation, they may state that they're using very strong cryptography, but in actual fact, it's not something that actually have bought or that is available to them. And the other thing, of course, is that when you interview personnel, it's basically human errors. You're going to encounter, not everybody is well-versed with cryptography, like the team here. Other people may not be so good at it. And there's one joke I heard. I thought it was just a joke, but then I encountered it myself in real life. So we were talking to this group of developers or programmers, and we asked them, is your thing encrypted? And their reply was, yes, it's encrypted. So we asked them, so where's the key? How do you generate the key? How do you exchange the keys? And they were like, we never exchange keys. I mean, it's this magical encryption system. It auto-encrypts. Then when it sends it to the other side, they decrypt by themselves without any assistance or keys. So we're like, this is amazing. So we took a look at it, and you can guess, what was this encryption? Was this magical thing called base 64? Okay. If you don't know what base 64 is, it's basically just a translation thing. So instead of binary, like 1101, you replace it with like ABC, so for transmission, for legacy system. And then when you reach the other side, because base 64 is a well-known standard, they basically take that ABC and translate back to 1101. For us, we know what it is. We can laugh at it. But for them, they can't tell the difference. I mean, for people who are not familiar with it, they look at the thing. The original thing was 1101, and then the output was ABCD. So as far as I'm concerned, I can't tell it's encrypted or not. So that's a challenge. Getting the answers from the personnel that's like trustworthy. And of course, when you combine those two together, plus the fact that some of these programs, these legacy programs, have like version 10, 11, 12. They're written by people who have left the company or years ago or something like that. It's a challenge to find which part of the code is actually in use, or what is it doing, or what is this actually encrypting. Combining all those things together, when you actually try to, as an assessor, you try to put these things together, you're going to get a lot of question marks. It's like you could figure out the algorithm, but then again, the algorithm, it could be those guys just reading documentation, and it says, license RSA Labs technology, and they give you that answer. But they have no idea what the key size or the purpose is. And for others, it's like they could just try to go into the system and look for the key file. And then they see the key file and they calculate, oh, this is like 512 bits, so I guess we are using a 512-bit key. But they have no idea what the algorithm or the purpose is. And lastly, of course, they might know that there is encryption in process, part of the package or part of the software, but they have no idea what algorithm or key size in use. So as a result, just before that, right? Yeah, okay. So as an assessor, PCI assessor, I mean, this is not something that's really rock solid proof that you can hold with it. It's sort of like if you look at the US presidential election thing, you have one side that's exaggerating the information or data, and you have another side who is using information from 10 years ago. So as a voter, you want a fact check. What's actually the truth? So that's what we try to address here. So with this, we introduce the next thing. And our idea is to find the fact check is to get the log usage. And how we do that is, well, before that, I would say there was this recent report from a major mainframe manufacturer in the world, and they claim that 87% of credit card transactions in the world are processed on the mainframe. So in other words, if we do this fact check, we can do fact check for about 87% of everything that's being processed. And trick here is to use this API that's inside the mainframe, basically an application programming interface. And this is how it comes together. So at the top here, we have our mainframe PCI applications, be it card generation or whatever. And in the mainframe, you have like these 4 different main languages like C, COBOL, Fortran, and PLI. And of course, if you're not from the ABBA generation, you probably have no idea what COBOL or Fortran is. So one of the things like the other session earlier, they were saying like, where they're talking about peer reviews. Okay, peer reviews is a bit difficult. I mean, peer reviews, if you know, you have a common understanding and you can actually check somebody else's code, that's fine. But the number of COBOL programmers, developers are very limited, and they're probably just specializing in, or they are doing all the COBOL programs, so they can't peer check themselves. And Fortran, similarly. And you can't get a COBOL guy to fact check a Fortran, you can't get a Fortran guy to fact check COBOL. Or they could, but it might take a long time, and they might not understand the code there. But the beautiful part in a mainframe is that all these PCI applications, regardless of the languages, to do the encryption and everything, they actually call this thing called the ICSF, Integrated Cryptographic Service Facility. And in this one, they actually specify the key to use, the algorithm to use, the key size to use, and the action and the purpose. So you have a lot of traceability there. And from here, this thing calls the HSM, which is like the session you saw before. It's like a hardware security module thing. And at the same time as it does that, it also generates a log. So there's a log recording of every action that it does, every single one of it. So here we have the possibility to get the truth, the fact check the thing. And of course, the problem is you can imagine a mainframe generates a lot of transactions, and especially we operate in so many countries, Estonia, Latvia, Lithuania, Sweden. And a mainframe is not the best place to do this kind of things. Main purpose is a transaction processing machine. So what we do is we actually gather these logs and do the analysis outside of the mainframes. And the current most popular way of doing things is this thing called a SIEM, a Security Information and Event Management. And this is a specialized software and server that basically is designed to absorb a lot of logs, huge volumes of logs. And normally they provide data analysis facilities to actually sift through these things. So putting together what I just said, so here you have the mainframes. Here is just 2, but the actual fact is about 10 to 20, depending on how big your bank is. And of course, for geolocational resiliency, these guys are purposely as far apart as possible, so they're not close together. So you have all of these dozens of mainframes all sending the huge amount of logs, so all coming in, and of course, nobody can process that many in one shot. It goes through the SIEM. And in the SIEM, basically, here we can actually filter out the things. So like what we mentioned just now, the ICSF. So we're only interested in the ICSF logs. That information is transmitted out to another platform, our artificial intelligence platform. And in here, I'll show you the results later and go to the details later. But briefly, it basically does some magic to the data there to create a meaningful summary. And that summary is actually sent to the PCI service owners. So this guy could own, or the owner of mainframe 1, mainframe 2, mainframe 3 kind of thing. From here, they can see from the report if anything is OK or everything is non-compliant or some anomaly that's happening there. And from there, they can actually click on it to view more details. They could go back into the CM. And inside the CM, because we actually keep all the logs there, you can see which mainframe application is doing it, what time it was being done, and who is doing it, who's actually executing this mainframe application. They could be, it could be a standard application, but somebody, when they started, they could insert some overriding parameters that makes it do some unusual stuff. So that AI block there that I showed, okay, I won't go into this. This is another session of its own. But essentially, in machine learning, which is a subset of artificial intelligence, one of the key things is this thing called ETL, extract, transform, load. So first thing is, of course, we extract the loads. We extract the logs that's related to the cryptographic thing, and we transform the data. So as you saw earlier, the algorithm and key size. So key size, it can be a bit ambiguous because you have key size for symmetric algorithm and key size for asymmetric algorithm. So if you actually have like 256-bit symmetric is considered strong AES, but then if you use 256-bit for asymmetric, it is a weak cryptography. So here we add all these values to it so that the AI knows the difference between all of these things. And then we load it back and run it through artificial intelligence algorithm. So actually, there are two algorithms we run through this pipeline. The first one is what we call dimension reduction, because here we actually have, now that we break down all this data, we have this bunch of data with too many data to look at. So we do a dimension reduction to reduce it to manageable. And this particular example you see at the end is that we reduce it to 2 parameters. So that's x and y, so that we can plot it on the chart. And from there, we ran another artificial intelligence algorithm, which is clustering, so that we can actually break it out to see what are the main things that all these mainframes are doing. So rather than completely you have no idea what these monsters are doing, now you can have one single image of what everything is happening. And of course, the thing is that we automate the whole thing. So it's not like you go to every mainframe and run this one at a time, because there's a lot of mainframes. So there's this automated system that basically kicks in. It runs it, right now it's pretty much a weekly thing. And it churns through the thing, generates the report, and basically an observation report, and sends it and emails it out to the relevant PCI owners. And of course, they will be supplied with all the information as well as the links to it. And we also create an archive of it, of previous observations. So the PCI owners can actually compare the latest scan or check with the previous one to see if there's any anomaly or unusual activity happening, or no activity happening. So if you're wondering what it looks like, this is what it looks like. Okay, this is of course not real Swedbank data, but these are these are things that happen in a mainframe. So starting from the right side, so this is what's, for each operation, these are the purpose, what is this thing doing? So for example, here you have assigning, and here you have verifying. And over here we have the key size. So it's like a 4096 or 2048-bit asymmetric. And here there's RSA, so we know that this is the asymmetric algorithm. And the other extra part here, this is above and beyond PCI requirements, or maybe in PCI 5.0. Because we actually go through the logs, we can actually check the number of times this has happened. So this is a beautiful part. You know what is actually important and what is not important. So if you're a PCI assessor and you need to make an exemption or you need to make a compensation for it, you could judge from it, because you may not be as lenient with this one, because this is a key operation. This could be running like 20,000 times an hour. I mean, you cannot afford to compromise anything like this. But here's something that's done only like once a month that maybe you could find a reason for that. And this is actually a good report. This is when everything is fine. Of course, conversely, it can be the worst case scenario. Here is basically a situation where everything is deprecated, and you have really old desk technology, and 64 bits. This has been broken. This has been broken by every other university PhD student. And this is good because it also reviews things that you may have overlooked. Because normally for this inventory, you actually look at the most important thing. Okay, the credit card processing, the payment. But you forgot about the third-party software or the supporting underlying libraries that you're using. And this thing actually reviews everything. So as an assessor, you can actually go there and find out what's actually missing and what's not reported. Finally, to put it all together, now you can see that there are a lot of information here. So that's where our AI kicked in. So this is not an eye test, but this is the visualization. Every dot here represents a transaction, a cryptographic operation on the mainframe. And here we basically consolidate like 10, 20 mainframes inside. So what you see here is that this is the most common activity. This is what is heavily doing day in and day out. And typically, this will be the symmetric processing. And these ones are further apart. So they are, in this example, they are not symmetric. These are asymmetric things. So these ones are very tightly coupled, so they are very, very closely related. That means the key size is similar, the purpose is similar, everything is very, very similar with maybe just minute differences. So this is most probably a backup encryption thing. And then some of these are just admin logins, there's usage here. And this one is interesting because this is kind of an anomaly thing. So this is encryption, but these guys are doing things a little bit differently. So this guy could be mostly decryption, and you're wondering why is this guy doing decryption out here? And as a PCI assessor, how is this valuable? Imagine this is the image we capture in March 2025. And in 2026, if we do this scan again, and this thing disappears, but the documentation and interview remains the same, what does that mean? It means that whatever that's documented and reviewed, whatever that's documented and reviewed is actually no longer in use. So something is out there, so you need to go and check with the people and the documentation. And the other hand, if in 2026, you get a big red patch out here, big red blob here, but your interviews and your documents remain the same, what does that mean? That means the mainframe is starting to do some new cryptographic operation and stuff, but it's not documented anywhere. And none of the people you're interviewing remember to tell you that, and there's no documentation applying it. So immediately, as a PCI assessor, you can spot it immediately. And you can go click on the CM, you can trace which application did it and who are the people who are doing it. And I'm out of time, so thank you very much.